Thank you very much. Thank you very much. It's a pleasure for me to be here, to visit Krakow again. I visited many years ago Krakow and saw that the city has very much evolved and developed. It's a pleasure to see this. And I'd like to thank the organizer for the invitation. So today I will speak and give us sort of an overview talk about what we do on gravitational-wave astronomy from the ground with LIGO, Virgo and KAGRA. So the objective of the talk here is really to give you some basic information of where we are and provide you some highlights about our recent observation and try to give you an outlook to what we plan for the future. I understand that in the room you are, I think, in great majority people from doing theory, theoretical physicists. So you may not be, acquainted with experimentation and what it entails. So I've tried to, insert information to let you understand what are the main difficulties we are facing and what we actually try to resolve when we are operating these large instruments that are LIGO, Virgo and KAGRA. So let's start with some very basic about gravitational wave detection and interferometric detectors. Unfortunately, there is a small animation, but interferometry, I presume you know. So we often present those interferometric detectors are Michelson interferometers. So this is a simple Michelson interferometer, and we detect gravitational wave by comparing the optical path, length, followed by a laser beam propagating in two directions. So this is what this interferometer does. It shines a laser light, divide into two, then come back and observe with a photodiode, measure the amplitude. And by doing this, we're comparing the rotten path that this laser beam does, and therefore able to couple this to the strain that a gravitational wave would create on the space-time of the optical path. So this is the simple explanation. This is the basic. Now, if you want to go to the sensitivity that you need to have for detecting gravitational wave from astrophysical sources, then you need to do a bit more than this simple interferometry, and you are led to a more complicated instrument than a simple Michelson interferometer. So let's see. So this is the schematics here. This is Virgo, okay? LIGO and KAGRA are slightly different schematics, but more or less we are doing the same techniques here, using the same technique. So those interferometers are dual recycled Michelson interferometer with fabric ferrocavity in the arm. So let's see what this means, okay? So this means that fabric ferrocavity in the arms, there are techniques essentially to recycle the light power into the interferometer as much as possible. Okay? Store the largest light power in the interferometer because it improves the sensitivity. We'll come back to that next. So how we do this? We do this by inserting mirrors. Okay? So those are the mirrors here, and these mirrors, they are creating optical cavities, so the light here is going back and forth in the arms, okay? And we store light power there, and we increase, in some sense, the optical path that the photons does inside the interferometer. So those are fabric ferrocavities, so the light here is injected in phase with the light that comes back, okay? So these are resonant cavities, okay? Okay, so this is one technique. Another technique are those mirrors here and there. Those are recycling mirrors, so this is a so-called power recycling mirror. And this is the signal recycling mirror. And again, those create resonating cavities that re-inject light in phase with the outgoing light, okay? So we re-inject here. So if you assume that we are on the dark fringe here, so no power or little power going out here, so this means that the laser light goes back to the bright fringe, so goes back to the laser source here, and we re-inject the lights in phase with the outgoing, the incoming light, okay? So this is the recycling of the laser power. And we do similarly with the output port here. This is the signal recycling mirror that I use. So you see, overall, those techniques are used and have greatly improved the sensitivity. Have been central for this for those instruments to reach the sensitivity that we have today. Okay. On top of this, there are, other characteristics that are relevant for those instruments that allows to achieve the sensitivity. So let's go through this. So first of all, those arms here, I'm sure you have seen photographs from the sky from those instruments. They are kilometric lengths. So here we have 3 kilometer length arms for Virgo, 4 for LIGO, 3 for KAGRA. Okay, we have optics here that I show an example of those optics here. Those are test masses, so those are the ones that are freely falling masses, okay, that we use to sense gravity. And those optics are exquisite optics, okay, made out of fused silica. Their surface are almost perfect mirrors for the infrared light. And you see we have an interest because of thermal noise. I won't go into those details later on, but we have an interest to have very massive test mass. So the best we can do today are tens of kilograms piece of very pure fused silica, as you can see. The laser are ultra-stable laser, and we are now using 100-watt laser, so it's a very powerful for ultra-stable laser. This is at the edge of what the technology can do. All the experiment here is suspended, so those mirrors here are suspended to isolate them from seismic activity of the Earth, the ground motion. And we are doing some, I would say black magic from the quantum measurement. I will go through this later on. We use this specific technique called squeezing that helps to shape the quantum state of photons that are circulating in the instrument. But you'll see how this can be done. Okay? So all those instruments have been taking data. So now we are operating the so-called second generation of detector. The detector infrastructure was built in the late 90s, and they have gone through first generation until 2015, and then there is this second generation that have started with advanced LIGO. So this is the so-called advanced generation, advanced configuration, second generation detector. So you see LIGO starting operation in this new generation of detector 2015 and taking data till today. So there are 4 major observation runs: O1 with only LIGO, O2 with LIGO and Virgo joining at the end, O3 with both LIGO and Virgo, and then new players are, so is KAGRA detector taking some data at the end of O3, together with GEO. I come back to GEO afterwards. And then there are, now we are going through O4. Right now, only LIGO is operating, and Virgo and KAGRA, as Adam said yesterday, will probably join later the run. So you see here, KAGRA is really entering operation now. GEO has been taking data for on and off for many years, almost a decade, and it is really used in case of major event in the galaxy, like the galactic supernovae. Okay, So this is a sort of a backup when this large detector here do not operate because they are in a grid. Geo is here to really make sure that we won't miss any major event. I forgot to say what are LIGO and GEO. Maybe there are people in the room that do not know. So we see an aerial view of the LIGO detector here. So two sites, one in Livingston in Louisiana and one in Hanford, Washington State. Distance 1,000 kilometers between the two sites. Virgo in Europe, close to Pisa, Italy. And then KAGRA in the Kanyokande mine in Japan. Okay, and then there is this smaller detector GEO, which is located close to another, which I described earlier, used primarily to astro watch mode in case of a major event in the galaxy. Okay, so those detectors have been improving in sensitivity over years, and this is what the best sensitivity that we have reached so far. So I'm focusing now only on Virgo and LIGO that have made a real observation and useful for detection of gravitational wave. So you see what we call the sensitivity curve here. This is what describes the ability of the instrument to detect gravitational waves. So this is a noise curve. Okay. So you see the noise is low here, a limitation of the observation of gravitational wave in this area, which is H. So this opens a window through between 30 Hz and a kilohertz for observing gravitational waves. It is limited here by seismic and control noises at the higher sensitivity, higher frequencies here by shot noise, and there in the middle by thermal noise. Thermal noise is the noise that comes from the thermal excitation of the atoms that compose the surface layer of the mirror. Okay? You can convert this sensitivity curve into an astrophysical measurement. Okay, so this is the so-called binary, the distance range to binary neutron star. So you assume your source is a pair of neutron stars, 1.4 solar masses. They collapse, okay, somewhere in the universe at a distance d, and leads a signal in the detector. And if this signal, we adjust the distance so that the signal to noise ratio of that source is 7. Okay, we know that with this number we have good chance to observe that source. So this defines the range. So you see with Livingston during this detector here, we were able to observe typical binary neutron star at a distance of 135 megaparsec. So, you know, I'm not sure whether you understand what's the neighborhood of our galaxy, but this is basically much further away from the galaxy cluster in which we are in. Okay, this is fairly typically, I think I would say, corresponds to several tens of thousands of galaxies. Okay, and you see the corresponding number for Hanford and Virgo. So what do we get those data? Okay, we have an observing run, we get large amount of data for months typical time scales, and we search in this. We search for many signals. I don't have time to cover all signals we search for, but we typically divide into categories. So we have 4 main categories. Either there are sources that we know, okay, that because we have a physical model for the source, okay. So we have a waveform, we have a signal, a reference signal to compare the data with. So this is either the coalescing binaries, okay, for which I will talk about, or it's also a continuous wave source or an isolated pulsars that emits gravitational wave because it's distorted. And here I like to note that there is a long and renowned expertise in Poland. The Polgraf group is really an international reference in this respect. And there are other types of sources that or signal we are looking at. So there are sources that we cannot model. Okay, okay? Either because we don't know or because they are too difficult to model. And there are either transient sources, so bursts of gravitational waves, or continuous sources like, backgrounds. And the graal here is really the cosmological gravitational wave background that arise from primordial cosmological ages. We are not going to detect these signals. It's not possible with the ground-based detector at those levels, but maybe we can detect a background of astrophysical sources. So a lot of astrophysical sources that are not resolved and that forms, by summing up, piling up, a real signal that maybe sometime, maybe soon, we could detect. Okay, so let's concentrate on this source here. And the way we do this is by comparing the data of LIGO, Virgo, and so on to a physical model. This is where your work in the room can be very precious to the science we do, because we need this astrophysical model to do the science and to analyze the data. So you see here for the coalescing binaries, you have these typical chirps which correspond to the frequency, orbital frequency rising with time and then finally merging into a single object. So this is this waveform model that we compare the data with, then we downweight with the noise sensitivity that we have and obtain what we call the match filtering time series that we use to detect the signal. Okay, and then the story of observation starts with the September 14th. I'm sure you know this event. So this was the observation of both the two LIGOs. That was the only detector operating at that time, which observed these very beautiful signals, 7 milliseconds apart. Okay, clearly associated, you can clearly see the chirping pattern here, 7 cycles that are associated with the merger of two black holes located at 400 megaparsec from here. So you see here another type of representation. So this is time and frequency, and you see the frequency going up like whoop, the chirping pattern. So after this first detection, there were many others. So during 01, there were 3 detections. During 02, there were 8 more detections. So we started building a catalog, GWTC, so the version. And another important event here is 170817 that Adam has discussed yesterday, the multi-messenger binary neutron star. And then there were many detections during 03, and if you sum up here, you get 90 sources. So I will go through those. So before I do this, I'd like to give you a sort of an overview of those 90 sources. So you see here different curves that present the cumulative histogram of those 90 sources. Okay, so this is 90. So you see that the slope at which we are taking cumulative detection is really increasing. This goes with the sensitivity and our ability to look further in the universe. Okay? And of course, you expect that this detection rate scales with the volume that you search. Okay? It scales with basically ignoring maybe cosmology. It scales with the co-moving volume, but really ignoring cosmology, since this is really a closed value universe with a cosmological perspective, it scales with the range to the cube. So you see here, if you plot the time volume here, instead of the time of observation and the number of detection, this is what we really observe. Okay, so this is 90 confident detection, all of them being associated with merging binaries, compact binaries. And I think the speaker that came to that conference last year, Keith Rice, gave a sort of highlight of a number of those sources that we've detected. I will only show a few. It's not useful to repeat what Keith did last year. What I will stress is what are, I think, in my opinion, what are the main questions that are really relevant and what about those 90 sources as a whole, okay? So, anyway, I start with an example anyway. So if you pick that source here, okay, so we represent that with GW and some kind of phone number, a lot of digits. So this is the dates and the time at which this event has been detected. Then, where we measure a number of parameters, this is what you see here. So a binary, a merging binary is characterized by 15 parameters as a whole, okay? But for astrophysical standard, for doing astrophysics, we only really are interested in the 5, maybe more parameters that we have here. So what do we measure? We measure the component masses, so of the two objects, their mass ratio. It can be useful for comparing with the formation of black holes models. The effective spin, which is a combination of the two spins of the two black holes, and then the luminosity distance of that source. And you see we are able to analyze this data here to produce those estimates with their error bars, which are represented here by their violin modes type of violin plot type of representation. So one, I think, very interesting case, very interesting signal is GW 15090521, so 21st of May 2029. This event is very interesting because of the masses that we measure. The masses that we measure, M1, the largest mass, has a mass that is definitely larger than 50 solar mass, and this is not permitted by current model for black hole formation. Normally, a star core, if you increase the core of the mass, the core of the star, will collapse and form a black hole, but because of the pair instability runaway process that can occur at some point when the core of the mass increases some typical mass, okay, the mass at the core will basically be blown away and no black hole should result. So what we expect from current models for black hole formation is to see what the so-called mass gap, high range mass gap, in which at some point we should not see any black holes above some mass of typically 50 solar mass. And this contradicts this model. So there is a lot of questions. This opens a lot of perplexity and a lot of activity in the astrophysical community to try to explain why we observe this. There are other interesting cases. So you see here, there are masses here that are much smaller. We barely see the uncertainty. So here, those are much lighter objects, typically smaller than 3 solar masses. So there is a clear indication that this could not be black holes, but probably neutron star. So those are, associated currently with binary of neutron star or mixed binary of black hole and neutron star. So those are interesting because there are so far very few objects we observe of that type. Okay, but as I said, what I will be interested here is to a view of the population as a whole. Okay, so what does these 90 sources tell us really on the population? So this really relate to a large population of heavy binary black holes that so far was unobserved. No other electromagnetic observation has ever observed those sources. And this raises many questions. How do they form? What are their environment? So the way we do this is by looking to the data, right? Looking to those measurements, those parameters we measure. So you could do this way. So here is M1 and M2, so the primary and secondary masses. And here this plot shows the median value for the parameter, okay, for all the sources as shown earlier, so 90 sources. And what you see here is that when you see patterns, right, you see accumulation here, some other cluster here, and then you see some tails at lower masses. However, if you want to infer a property of the population of black holes as a whole, and not the population of observed black holes, you need to do some more work. Because, of course, there are selection bias, okay? Our detector do not detect any black holes. We see more massive black holes further away, more lighter black holes, we don't see them further away, okay? So this leads to some bias that we need to compensate with to be able to count black holes per unit volume of universe, for instance. So you need here to do some more work, and this is what we do here. So first by considering the error bars as well, so you need to fill uncertainty in. And this is what we do between these two plots here. So this is the raw data, okay, and this is the distribution in mass, or in short mass, of the observed black holes. So you see here there is some kind of accumulation point, but really to conclude whether this is a real accumulation point, you need to compensate for the selection effects, and this is what we do here in this curve. So what do we conclude from this curve is that there are indeed two accumulation points, one here, which is very significant, and another one here, which is a bit less significant, okay? And there is maybe another one here that, well, I guess we'll conclude about this one after we take the data of O4. There are also depletion of that curve. So here, it seems that there is some missing black holes happening in this range, maybe here as well. But what we also conclude is that we don't see a gap, okay? We don't see a real stop in the distribution of black holes going to higher mass, contrarily to what the theory of black holes formation tells us what we should have expected based on this. So this is it. What we are able to do is to measure the merger rate per unit volume. So we have an example here. And we are also, with 90 sources, we can also distribute, have some kind of indication of how the merger rate evolves with that shift, okay? Which will be very interesting at some point when we have enough statistics, because we'll be able to compare this merger rate with the star formation rate, okay? And there should be some correlation between the two. So this is a very active area of research. It's very interesting to follow this science. So I move on to some other scientific results we produce. We produce, I think, maybe interesting for you that are specialized in relativity and this type of sector of science. We do tests of the theory of general relativity with our data. So for this, we really select the golden plated event by making a much more strict selection on the event we use for those tests. And we use a range of, we test a range of effects, okay, predicted by general relativity. So we do waveform consistency tests. So basically, we subtract the prediction of general relativity from the data, and we look for residual, okay? And if there is some kind of residual, this means that maybe some part of the signal is not predicted by general relativity. And this is done here. So here, to each residual, we attach a probability of that residual to be explained by the noise, okay? This is a p-value. And we plot here the distribution of the p-value for the 90 events that we've collected, okay? And what we compare this p-value with some random draw, okay? We expect this to be some uniform distribution between 0 and 1. And this is exactly what we see. So here, the observation that we see is that general relativity passed the test. We also do some internal consistency test of the waveform. So we take a part of the signal and see whether the remaining part of the signal is compatible with the parameter that we have estimated with the initial part. So here again, this is an internal consistency of general relativity, not general relativity, but of the signal predicted by general relativity. We test the generation of gravitational waves, so by parameterized test of the post-Newtonian approximation of the model of the signal. So leaving a freely post-Newtonian parameter and see if they are consistent with what post-Newtonian theory explain or predict. We test the propagation of gravitational waves, so we measure the dispersion relation of gravitational wave. We test the polarization of gravitational waves, whether they have two polarization or more. We test the property of the remnant, so the nature of the remnant with respect to what we measure with the initial part of the signal. So the written part here, this is the measurement of the mode, the 2-to-1 mode frequency extracted from the ring down, and here we measure the difference between what this mode should be based on the value we measure from the initial in spiral part of the ring down of the signal when the two black holes are far away, and so when the two black holes are far away, we were able to measure the masses and therefore to predict what will be the final frequency. And we measure this frequency independently from the ring down, and we compute the delta between the two. So this, we see here that the agreement is basically at 1% compatible with general relativity. I'd like to have a note maybe for you, if you are working in the area of modified gravity theories. We really lack currently models and waveform models based on modified gravity theory. This would enable us to test those theory directly with our data. Currently, this is something we cannot do. So I don't have time to describe everything. You see, those are all the tests we do. This is all the events we've checked with those tests. There is a paper, a very nice paper here that does the full summary. The conclusion of the paper is that there is no evidence for departure from GR. All the results that I've shown are produced with, of course, from data, and these data are now freely available. They are freely available on this GWOSC website, so Gravitational-Wave Open Science Center. So there is 15 terabytes of data that are available to anyone. They are available under the free license, the CC BY. We offer the gravitational wave data, we offer the event catalog, documentation, and software tools to help you to analyze the data, access the data. There are workshop tutorials that you can join if you are interested in. There were a recent data paper, so a paper that gives the full description of the gravitational wave data from the O3 science run. Okay, so let me switch to the second part of my talk, so the outlook, so where we are now, maybe status and outlook. So we are now here, O4, so therefore starting a new science. So this was the initial sensitivity curve that was promised, expected for LIGO-04, 60 to 190 megaparsec for the BNS range for LIGO, and 90 to 120 for LIGO. We are not completely there yet, but LIGO has made very good progress and is really taking very nice data now. So this upgrade is the result of a lot of work, 3 years of upgrades, where many parts of the instrument has been changed. I'm not going through the full details here, but I will outline a few very important points. First of all, there were a major upgrade of the laser source. Right now in LIGO, there is the laser power that circulates inside the interferometer has been doubled with respect to the past. So there is almost half a megawatt of light power circulating in LIGO. This is amazing. This is completely mind-blowing. We've been successful with the frequency-dependent squeezing, and we'll give some more detail later on. And here in Virgo, we've been installing a new signal recycling mirror. LIGO has it for many years. This is new for us. We are trying to learn how to make this to work. In fact, this is maybe one of our major difficulties now. And also on the KAGRA side, there were resolving major limitations with respect to limitation of their harmonic. I can come back to this if you're interested. But the bottom line is that unfortunately neither Virgo and KAGRA were able to join LIGO earlier this year on 04. It will be delayed. Hopefully we'll join next year. So let me pause just a minute and explain what this quantum frequency, this quantum squeezing is. I think it's very interesting. So the quantum noise here is in the interferometer is basically related to quantum fluctuations of the electromagnetic fields that enter the output port of the interferometer. This is how quantum mechanics describe this effect. Okay, so those quantum fluctuations enter the interferometer, interact with the interferometer, and then result in a quantum noise that is measured by the photodiode. Okay, so what are the quantum observable? There are two quantum observable. One is amplitude and the other is phase, and they are associated with two conjugated quantum operators. So the coherent state, the ground state of this quantum system is basically a zero amplitude and equal uncertainty on phase and amplitude. So this is in the phase amplitude plane, this is a circle, okay? Equal uncertainty on both axes. Okay, so the idea here is that this quantum shape we can tune, we can modify, we can squeeze the circle into an ellipse that will reduce the uncertainty on an axis at the price, inevitably, to increase the uncertainty on the other axis. Okay, so this is the principle. How can this help? So at high frequency, there is the shot noise. The shot noise is the overall dominating noise, okay, which is part of the quantum noise. And this is related to phase quadrature. So we have an interest to reduce the uncertainty of the phase quadrature at the expense of an increased uncertainty on the amplitude axis. Okay, so this is what we do by doing squeezing. And therefore, we were able to do that for many years now and observe a reduction of the quantum noise at high frequency. But now we are observing, a degradation of our noise at low frequency, and this is because of the radiation pressure noise, which itself is coupled to the amplitude quadrature. So there is a trick. The trick is frequency-dependent squeezing, in which instead of squeezing, in which you squeeze the phase axis at high frequency, and then you turn the ellipse to squeeze the amplitude axis at low frequency. Okay, and this is possible. This is possible by an addition optical scheme, which I won't detail. But this was successfully demonstrated for the first time a few months ago. So you see here the LIGO sensitivity curve. So this is the black one with no squeezing. The green one with standard squeezing, so only phase squeezing. And you see here that you increase the noise at low frequencies, so not good. And then there is this new scheme of frequency-dependent squeezing where you get the improvement at high frequency and you get the improvement at low frequency. This is remarkable. It means that now quantum techniques are really, standard method in gravitational wave astronomy. So to measure those huge objects, okay, black holes, hundreds of solar masses, you need to tune the quantum state of photons to ensure that measurement. Okay, so there is this picture of the, I think, historical picture of the 5 interferometer together. So why? Because at some point KAGRA and Virgo was doing taking some data during June. So it's, I think, it's for a group picture basically. But we are waiting for those two detectors here to enter the real game in 2024. But so far, I think Adam said the summary, so LIGO has been observing, okay, for many months now. You see typical BNS range is 150 megaparsec. Observing time 77 part of the time. It's a very good result. Duty cycle. Half of the time we have 2 detectors working, and you see some data points that are related to Virgo. Okay, what we do, but here again, Adam discussed that yesterday, we do low latency analysis, so this is to allow for follow-up observation, maybe turning telescope and see that part of the sky that relates to that particular event. So we emit those alerts, gravitational wave alerts. I won't repeat what Adam said yesterday. We have 40, I think we had one alert tonight. You can see this is open data, okay? So this is, you can go on that website here and see what we are observing. Typically speaking, we observe a rate of alert that is twice what we observed during the past time. 1 every 3 days. So this is a typical alert. So you see this event that was observed on August 11. There is, of course, LIGO here. Adam explained that very nicely yesterday. This localization in the sky of the source, the typical distance. There is a message that explains what we've seen, so on. Let me move on to the outlook now. So we were here, and now we are moving here. So what's next? Okay, 05 and post-05, which is not in that. Okay, so what's next? Well, first of all, we have plans for 05, so the run that will occur after the current run 04. This is planned for 2027, 28. I think the date is not completely fixed yet, of course. And well, so this is funded time. So this is going to happen. We have the funds to do so. The goal is to have an improvement of 1.5 with respect to the astrophysical range that we have now. And we'll do this by using better mirror coating. So the surface of the mirror is obviously very important. Okay, this is where the light interacts with matter. So we need those coatings to be to have the best elastomechanical property. So there is a lot of research being done here. Increase the laser power, use larger beams, and therefore larger mirrors. All this research is, already going forward, and the mirrors, the substrates for the mirror, so the piece of fused silica, have been ordered already 1 year ago. There may be a major upgrade that will occur in Virgo. We have, I think this is what slows us down very much currently. So we have a slightly different design for the recycling, so for the fabric pleural cavity in the arms. Those in LIGO, they are so-called stable cavities, which resonates only one mode of the laser, the 0-0 mode. Here in Virgo, we have another design where 0-0 mode resonates also with other higher order modes. So this is an issue. We knew this we expected that this would work anyway. And first of all, it would cost 20 million euro to implement those stable cavity. So we decided 15 years ago that we won't do this because it was too expensive. Now we realize that we were wrong. So maybe, and possibly, likely, we'll have to spend that money and implement stable cavity. And then we are working on post-05 plans. So what is going to happen after 05? Not firming yet. Another factor of 2 of improvement in science reach, and therefore a factor of 8 in volume. Okay, and those projects are called A# for LIGO and Advanced Virgo Next for Virgo. We are at the conceptual design stage, and we are working on the technical design. And the target here is to have something in the early 30s. Because afterwards, we'll be moving to the third generation. And the third generation is in Europe, Einstein Telescope. I'm sure you are aware of that very large project. So the international collaboration is separate from Virgo. It has been formed last year. The objective here is to build another infrastructure, 10 kilometers long arms, underground, cryogenic, could be with a special triangle optical scheme. The science with a target of an improvement of tenfold improvement with respect to those instruments that will operate in 05. So the expectation, science expectation from Einstein Telescope are enormous. We expect to observe 90% of all black holes merging in the universe. There is a very good news that has happened recently, is that the government of India has approved the LIGO India project. So there will be a detector in India that is basically a joint venture with the American. So they are already building the infrastructure. So, but there is a green light for the government to proceed. Conclusion. We've been doing three observing runs with almost 2 years worth of data. 90 sources has been detected, revealing this large population of heavy black holes that was not observed earlier, that raised a lot of questions, a lot of very interesting questions about the formation of those objects. There were 3 years of upgrades with a big success of frequency-dependent squeezing. The O4 run just started in May with a very good range. There is a lot of data coming in. I really hope we'll see Virgo and KAGRA joining at some point. And then there is a very ambitious program for the future, 05, post-05, a transition to the third generation. And more generally, I think a lot is happening on gravitational-wave astronomy in general. So I've been talking about this small part here, around 100 Earths of the gravitational-wave spectrum. But you may be aware that LISA is going through a path of adoption this year. This is a very important event for our community, with potentially a detector that will observe the merging of supermassive black holes, as we heard yesterday. There is also the big result that was obtained by the pulsar tiny array community at the nano-Earth region. And with this, I thank you for your attention.
So let's open the question.
First of all, thank you for your result. And I actually have two questions. So the first one is that you mentioned at some point that the statistical analysis of the events shows no departure from general relativity.
Yes.
And I was wondering if this is a strong argument against modified physics of gravity, or if, as long long as the theory of gravity keeps GR as a certain limit, it should still be an acceptable theory?
Well, I think your question is about how science is fundamentally working. What we show here is that we have results that are compatible with general relativity, and until this is the case, what we can conclude is that it's either general relativity or some other theory that is making observations that are compatible with what we observe. So we cannot exclude any theory. I mean, this was my point actually. We cannot exclude any modified gravity of theory unless we have a prediction from that theory. And this is why we are not able to exclude those theories today, because we don't have a model to compare with.
And,
I'm not sure that I got
no, I
this.
understand, yes. And another question, this might be a little basic from my side, but you also mentioned that the theory of black hole formation somehow predicts a mass gap after 50 solar masses, and I'm wondering where does that gap comes from? Because even though we know that black holes form in a certain mass regime for, I don't know, stellar collapsing, etc., you still expect to have a longer range of masses from black hole coalescences. So why would we expect a mass gap after 50 solar masses?
So why do we expect a 50? Maybe actually you are more qualified to answer that. Maybe I can give it a try and you can complement what I say, because I think Tony is more aware of this. So basically what I explained is that the formation of black holes really depends on the initial state of the progenitor star, okay? So these progenitor stars have a core and outer layers, okay? And depending on the mass of the core, certain instability may develop or not, okay? So the current theory of black hole formation is that there are instability that are related to pair formation, electron-positron pairs, that develops and create runaway processes in which the core at some point does not collapse anymore, but basically is disrupted, okay? And therefore there is no black holes being formed. And the theory predicts that well, this occurs to cores of stars which are, I don't know, few hundreds of solar masses, okay? And therefore, the highest mass black holes that you could possibly form is a bit smaller than those few hundred of solar masses, but will result in the maximally massive black holes of 50 solar mass, okay? So we have this expectation that above that 50 solar mass, we don't observe any black holes anymore, where actually this runaway process prevents the formation of black holes, but then at some point with even more massive star, then we can form black hole again. So there is some gap here that we expect to see in our data, and this observation contradicts this prediction. Did I get it right?
Yeah, I fully agree. This is
But would we expect any way to see black holes in this range formed by coalescence of smaller ones?
yes.
Yes, okay, so, right.
So why would we still expect a gap if we know that black holes in this range can still form from coalescence?
Okay, so I see where you are coming in. So that's a very good comment. Okay, got it. So yes, so one of the scenarios that are brought forward, okay, is that this could be hierarchical mergers. So two black holes that merge, then that forms a black hole that indeed is larger, have a larger mass than 50 solar masses, but then these black holes ends, and then somebody meet, and then suddenly meets another black holes, and then merge again. But you understand that for this to happen, you need to be in a very special place of the universe where black holes meet very often, okay? Because usually in the galactic field, black holes don't meet very often. So this is going to happen in very dense and heavily populated region, maybe galactic nuclei, maybe globular clusters, but then it's all related to a dynamical model of those very dense regions of the galaxy. So there is some more astrophysics to make this work.
Yeah, so these objects that is mentioning, so dynamical captures, those could happen indeed, would have larger mass black holes, but the signals that the LIGO is detecting, and maybe there is a bias on that because of our models of waveforms, all show the presence of a shared signal, and those wouldn't be there if you have a dynamical capture. So the systems we are detecting are quasi-circular binaries, and those are formed through standard stellar evolution with LIGO. So, and in addition, this very stability supernova gap, there's plenty of uncertainties there. So the mass gap is not really very clear, and the physics there is also perhaps not entirely understood. And the supernova models are very complicated as well for numerical explosions of stars. So I would say there's still plenty of margin for improvements in those models.
So I understand that so far KAGRA is the only detector which is underground. Does it make any important difference? Or was it, the reason that the Einstein telescope is also planned to be constructed underground is maybe just because it's difficult to find so much space on the ground?
No, it's not the reason. Well, it's not the only reason. It's true that you're not you don't care with roads and other problems that we have on the surface. But an important major reason for going underground is also the fact that seismic wave and ground motion activity is a surface activity, is a surface waves. Okay, so going underground, and if you put a seismometer at the surface of Earth or in a mine, you get a totally different picture. It's much more quiet underground. So that's another reason why. And of course, those are remote places, so you get less anthropic activity. This has a price. Well, you need to construct a tunnel, and this is very expensive. And it's actually not completely trivial to operate underground. KAGRA has a lot of problem with water. There is a lot of water underground that flows continuously, and this is very difficult. There are, very difficult, a lot of difficulties because of that.